Here we go with a review of quadratics. We're going to start with our basic x squared, and just remember that our x squared graph looks like a U-shape, and we grow in the rate of over 1, over 1, up 3, over 1, up 5. That's just the standard growth rate of any quadratic with dilation of 1. We learned that the axis of symmetry, the line that splits the graph here in half, takes the equation minus b over 2a, and that the domain of all quadratics will be negative to positive infinity, and the range depends on where the vertex point is. In this case, the vertex is at 0, 0, so the range, we would write the range as inclusive 0 to positive infinity, non-inclusive. In our vertex form of the quadratic, we have these three variables, a, h, and k, that affect it in different ways. The a is our stretch or compression factor. It's also the orientation factor. I call it the fun factor in class, where if a is negative, we get a frowny face, and if a is positive, we get a happy face. And the vertical stretch happens when a is greater than 1, and the vertical compression happens when a is between 1 and 0. We also learned that hk is the vertex point in our vertex form, and h turns out to be the axis of symmetry. Also, we learned that the horizontal shift, h, is opposite of what we think. So in our equation, it's minus h, so when it's x minus 2, we shift to the right 2. If it's x plus 2, we shift to the left 2, because h is negative. Now, k is friendly. K is what it is. So if it says plus something, then it's above the x-axis. If it says minus something, it's below the x-axis. These are other two forms that we've seen, general form and intercept form. In another video, you'll see how we convert to all three forms. Now, in this slide, I've put together a horizontal and a vertical shift. Since h says 2, we have a shift of 2 to the positive side, and we drop down 3. And our axis of symmetry is here, right at x equals 2. And we always want to put in our vertex point and then our domain and range. Again, range is dependent on where our vertex point is. In this case, it's at includes negative 3, but not positive infinity. Also, I wanted to show you just the algebra involved in finding the y and x intercepts. The y-intercept simply putting 0 in for x, and then using our order of operations to find the value of our y. So our y-intercept's at 0, 1, and then our x-intercept, we set y equal to 0, and then we just backsolve. Again, inverse operations, we undo the equation, so to speak. Since it's minus 3, we will add 3. We'll undo the square by square rooting, and when we square root, we have a plus minus the square root of 3. And then the last step is just to add our 2 right up here, and we get our two intercepts, 2 plus root 3 and 2 minus root 3. Now, the next slide is going to show you what happens when we find the averaging the intercepts or the axis of symmetry. We're going to add these two values together and divide by 2, and we should end up with this x equals 2. And I'll show you the math in the next slide. So when we average the intercepts, we just add them and divide by 2. And what we end up with is that center line of the graph. And this is going to help us when we start converting intercept form into vertex form, which you'll see in the following video. In this example, I've put in a vertical stretch, growing twice as fast as the normal parabola. We've shifted 3 this time to the left since it's plus 3, and we've dropped down 6. So vertex point is here at negative 3, negative 6. You can see the domain and range. And now, instead of growing by over 1, over 1, up 3, over 1, up 5, we go over 1, up 2, since we're growing twice as fast, over 1, up 6, and then the next one would be over 1, up 10, and so on. So we just need to keep that in mind, that the bigger the number, the skinnier the parabola will be. And then again, here are the y and x intercepts, the algebra involved. This one's a little trickier because you have to first do the power and then multiply it before you can subtract that 6. And then for the x-intercept, you just need to remember to get rid of that coefficient. So again, we're using inverse operations. We'll add, subtract first, multiply, divide, and then take the square root, and we end up with this answer as your x-intercepts. Our final example has a compression. A value is between 1 and 0, and in this case we're growing 1/3 as fast, or it's a compressed or squished graph. So instead of going over 1 up 1, we go over 1 up 1/3, and instead of going over 1 up 3 from the next point, we're going over 1 up 1, because 3 times 1/3 is 1, and so on. So that's why it's only growing as third as fast. Again, always label the vertex point. The axis of symmetry goes through the h value, and then here's our domain and range, and then here are the y and x intercepts, the algebra involved. Again, it's tricky. If you don't like working in fractions, we just need to remember when we multiply a fraction to a whole number, you can leave it as an improper and then just work with common denominators, or I could have made this a mixed fraction and then subtracted 3 wholes from the mixed fraction and still end up with the same answer. On the x-intercept, what's tricky is how we get rid of this 1/3. So to get rid of a 1/3, we just multiply by its reciprocal. So I multiply both sides by 3, and we end up with 9 on one side and 1 over here. And then when we take the square root, we got the positive and negative value. And then we just subtract the 4. So we got -4 plus 3, or -4 minus 3. Okay? I hope this was helpful, and we'll see you in the next video.